At this point, we can solve any system of linear equations. We can write it as an augmented row matrix and then reduce that row matrix using Gaussian elimination to reduced row echelon form, and then we can read off all of the solutions to that system of equations. So you might be wondering, what is there left to do when it comes to linear algebra? Well, it turns out to get a deeper understanding of the collection of solutions to systems of linear equations, and to get a deeper understanding of what exactly a system of equations is doing, we need to set up some notation and some operations having to do with matrices. So let's have a look at some terminology and notation. So for any matrix, remember we use when we list the size of a matrix, the row always comes first. So any general, arbitrary matrix will be called m by n, although we might use different letters in different contexts if we need to. But the number of rows is always first. Just like we usually call a function f, we'll usually call a matrix A unless we need a different name for it for some reason. So m by n matrix A looks like this. It has n columns and m rows. And sometimes, just to abbreviate things, instead of writing out its entries with dot dot dots like this, we'll just abbreviate it using square brackets to indicate it's a matrix, and little a sub ij just to the little a sub ij is just our way of writing the ijth entry of A. So the entry, the number that's in row I and column j. So when we put this in square brackets, this is just sort of an abbreviation to say all of the entries of A that are, in a matrix. The rows and columns of a matrix will turn out to be important for some applications. So the ith row of a column is just the ith row of a matrix is just all of the entries that are in that row, and the jth column of a matrix is, of course, all of the entries that are in that column. We'll have some use for referring to the columns of a matrix on their own, and so we'll actually give these columns a name. We'll call each one A sub j. You might notice that these columns, this is really just a matrix that's m rows by one column. This looks basically like a vector, and indeed it is. There are sort of two ways to get vectors out of matrices. One is just have a matrix that's n by 1, and that gives you what's called a column vector with n entries. And the other is to have a row that's a matrix 1 row by n columns, and that gives you what's called a row vector, like this. In general, when we write vectors, we will write them as column vectors. So these look very similar, but there's actually a conceptual difference between these that's kind of important to keep track of. So in general, when we write vectors, we'll write them as column vectors, and do not just think you can replace a column vector with a row vector. They will behave differently in the topics to come. So in general, we're going to be working with column vectors. All right, so that's just general notation for matrices. But what is it really that a system of equations is doing? Well, think about a single equation for a single variable like this. One way to think about what this is doing is that we have a left-hand side that's a function. Here we might call this function f of x, and it's x squared minus 3x plus 2. And this function has an input, which is x, and then it has an output, which is x squared minus 3x plus 2. Right, so a function transforms an input to an output, and then this equation looks like f of x equals 4, and we want to find the input that makes this true. Okay, so this is just translating an equation into a statement about functions. Find the input for which the output is 4. Thinking about an equation this way is an advantage because once we have the concept of a function, we can then do operations with functions. We can multiply them, we can divide them, that sort of thing. So what is the corresponding idea for a system of linear equations? Well, a system of linear equations isn't just one equation, of course. It's many equations, and it's not just one variable. In general, it's many variables as well. So if we wanted to treat the left-hand side of this system of equations as a function, what sort of function would it be? Well, remember the variable counts as the input for a function. So the input is is your variable, but here we have many variables. So it's not just x1 that is the variable, it's also x2 and x3 all the way up to x sub n. So these are your inputs, or your input. Since there are many of them, we need to package them up somehow, and so we can package them up as a vector like this, a column vector in particular. And so this left-hand side does something to all of these values for the variable and produces an output. And the formula that, it uses a formula to tell you what the output is, and the formula is a11 through times x1 plus all the way to a1n times xn down to am1x1 plus plus amnxn. So here's the output that this function produces, and then the system of equations just becomes solving the system becomes answering the question, what input produces the output b1 through bm. Okay, so our input is thinking of it this way, we have some function that takes a vector as an input, produces a vector. I guess this vector is an n vector, column vector, produces an output with m entries. So this is an m vector. And the system of equations is now asking what input, n vector input, produces the m vector output, b1 through bm. Thinking of systems of linear equations this way will let us do the same thing with these sort of vector functions as we did with single variable functions before. It will let us combine them in various ways. And that's what we're going to look at next. What are the various ways that we can combine these kinds of functions? Of course, when we represent these kind of functions, we don't actually write out all of the variables because you don't need to write out all of the variables to know what this function is. If we know that this vector function is linear, all we need to write down is the entries or the coefficients, in other words, the matrix. So when we do operations with linear vector functions, we will do those operations by manipulating the matrix corresponding to the linear vector function.